Today's lecture will give you an outline of intermediate value theorem, which is a very significant theorem when we deal with continuous functions. So the statement says that suppose if f is a continuous function on closed interval ab and c is a number which is coming inside f of a and f of b, like this. That is either f of a strictly less than c strictly less than f of b, or f of a strictly greater than c strictly greater than f of b. Then there is some point x naught in open interval ab such that f of x naught is equal to c. So to see it as a graph, suppose consider a is equal to 0 and b is equal to 1. So this is our interval 0, 1, closed interval 0, 1, and we are defining a continuous function. You can see this function f is continuous because we can draw it without lifting a pen or pencil from the place we are drawing. So this function is continuous. Now this is our f of 0, right? And this is our f of 1. This value will be f of 1. Okay, you have to take a c which is strictly in between f of 0 and f of 1. This is a case. Okay, then we are saying that if suppose we are choosing such a c, we are able to find an x naught inside this domain, that is which is not 0 and 1. This x naught is strictly in between 0 and 1, such that this c is equal to f of x naught. So this is just the intermediate theorem. So if such a c exists, then this x naught is existing such that f of x naught is equal to c. Hope you have understood what the theorem implied using this graph. So in geometric terms, this theorem says that the graph of a continuous function to pass from one side of a horizontal line to the other, the graph must meet the line somewhere. Okay, to understand that, consider the figure 3.1.4. You can see a function which is plotted, which is drawn, and you know that the function is continuous, right? And this is A, this point is A, this point is B, and you know this point will be f of A and this point will be f of B. You are choosing a C in between this f of A and f of B, call it C, okay. Draw the straight line at C parallel to the x-axis. See, this is the straight line, and this straight line will be called y is equal to C, right? Okay, and this point will definitely intersect at this point. That's what the intermediate value theorem says, because that point will be the corresponding x naught which is lying inside A and B in between, such that f of x naught is equal to this C. So in geometric terms, this theorem says that the graph of a continuous function will pass from one side of this horizontal line to the other by intersecting or meeting the line somewhere, right? And we can see example 6, which asks us to find or show that there exists a number x naught such that x naught raised to 5 minus x naught is equal to 3. Obviously, we have to use the intermediate value theorem because this is something related to that. So for that, you are having x naught raised to 5 minus x naught in the LHS. Okay. Treat it as a function. Okay. Treat it this as f of some f of x naught. Okay, this LHS. So because this is f of x naught, we have to define like this. So we have in general to define f of x is equal to x raised to 5 minus x, all polynomial functions are continuous. That is an important note which we had dealt with before. All polynomial functions are continuous. Polynomial functions are rational functions with denominator 1, right? All rational functions are continuous. So in particular, all polynomial functions are continuous. So this function f of x is also continuous. Now we are just finding two numbers which is lying in between this 3, or I'm just choosing uh, say, you know that 3 is a positive number, so you have to choose two numbers. You have to choose two numbers such that both numbers are lying on the other side, on each of the sides of 3. So for that, we are choosing f of 0 is equal to f, we are finding f of 0. Then when you find f of 0, you get it to be 0, and we are understanding that this 0 is on to the left of 3, so we can use it. And then you just find f of 2, or if you're choosing f of 1, you know that the function will be showing 0, right? So we don't have any use. Then you find f of 2, right? F of 0 you got it to be 0, f of 1 it is 1, f of 2 you are finding. F of 2 when you found out, you got it to be 30. So you understood that 0 and 30 are useful because 3, the number 3 which is lying here is in between 0 and 30. Okay. So you have this one, f of a strictly less than c strictly less than f of b. This is what we got now. F of a is nothing but f of 0, which is 1. F of b is nothing but f of 2, which is 30. And c, you know what is it? It is 3. So sorry, this is 0. F of 0 is 0. So this is what we obtained. 0 strictly less than 3 strictly less than 30. Now since our function is continuous and this 3 is lying in between 0 and 30, intermediate value theorem says that there exists a number x naught in between the domain point 0 and 2 such that f of x naught is equal to 3. So our question is solved, and note that f of x is equal to x raised to 5 minus x is continuous on the whole domain. All polynomial functions are continuous on the whole domain. So in particular we can say that this function f is continuous on, we are choosing 0 and 2 here, right? So you can say it is continuous on closed level 0 2 and choosing it to be 0 30, right? You can choose like this, and that will essentially imply that such a number x naught is existing. So this intermediate value theorem is not telling us how to find the number x naught, but it essentially helps us to guarantee the existence of such a number x naught. Now example 7 says that we have to find a solution to the same equation we just dealt now, x raised to 5 minus x is equal to 3 in open interval 0 2 to within an accuracy of 0.1. You have to find a solution with an accuracy of 0.1 by repeatedly dividing intervals in half and testing each half for a root. Root means a solution. You have to find a value of this x such that this is happening. Okay. So in example 6, we saw that the equation definitely has a solution inside the interval open interval 0 2. That's what which we mentioned here in example 6. So you have to locate the solution more precisely. So simply evaluate f of 1. As earlier we said, it is equal to 0. And you know f of 2 is 30. So you have f of 1 is strictly less than 3, strictly less than f of 2, that is fine because this is 0 and this is 30. So this is fine. That means by intermediate value theorem there exists a solution inside this 1, 2. Then you can bisect this closed level 1, 2 into 2. 1, comma 1.5 and 1.5 comma 2. Okay. Then find f of 1.5 using your calculator. F of 1.5 will be 1.5 raised to 5 minus 1.5. That will be approximately 6.09, which is strictly greater than 3. And you know that f of 1 is 0. So this is strictly less than 3, and this is strictly less than f of 1.5 because this is approximately equal to 6.09, right? So that means there exists a root inside this interval, right? Now again we are bisecting this 1 comma 1.5 into 2. So first what we did, we divided 1, 2 into 2 intervals, 1, 1.5 and then 1.5, 2. And we said that the solution is lying inside this interval. Now we are going to split this interval into 2. So that will be 1, comma 1.25 and then 1.25, comma 1.5. Okay. For that, first you are finding f of 1.25. You got it to be 1. You will get using your calculator. You get that to be equal to approximately 1.80, and you know that f of 1.5 you already calculated, that is approximately equal to 6.09. That means f of 1.25 strictly less than 3, strictly less than f of 1.5. That means existence of a root is guaranteed in the interval, closed interval 1.25 comma 1.5, right here, 1 point in the open interval 1.25 comma 1.5. The existence is guaranteed here using intermediate value theorem. And then you again bisect it into 2, the corresponding interval will be open interval 1.25 comma 1.375, and thus we can say that by bisecting again and again, this x naught will be lying inside this interval. So we are just approximating it to be x naught to be equal to 1.3 because that happens to be inside 1.25 and 1.375. So you can approximately give the value as 1.3 because 1.25 is approximately 1.3 and this is also close to 1.3. So you can give a better accuracy if you are making mode bisections. So if you have anything related to this question, any clarifications, you can uh, just go through again and clarify with me. And also you have an contrapositive statement for intermediate value theorem, second version, which says that suppose f is a continuous function of closed interval AB and no value of x inside the domain is having the value c. That means if f of a is strictly less than c, f of b will also be strictly less than c. Similarly, if f of a is strictly less than c, then f of b will also be strictly greater than c. Sorry, both will be greater, both will be less. So this can be seen in this figure. That is, if c is a number which is coming above all the functional values, and if we are drawing the line, the function will lie entirely on one side of the number c, y is equal to c, or the line y is equal to c. That's what the theorem gives us in a geometrical manner. So this theorem second version says that the graph of a continuous function which never meets a horizontal line must remain on one side of it. First version says that if the graph of a continuous function passes from one side of a horizontal line to the other, the graph must meet the line somewhere. So that's what the geometrical meaning of both the intermediate value theorem 1 and 2, first and second version says, and that's important for you to understand. And example 8 asks us to uh, prove something. Suppose f is continuous on closed interval 0, 3 and f has no roots on the interval and that f of 0 is equal to 1, prove that f of x is strictly greater than 0 for all x in closed interval 0, 3. So here we are using the intermediate value theorem version 2. Okay, we have to prove that f has no roots. That means we have to say that the f doesn't pass through that horizontal line we are going to choose. Okay, so the a function has roots if f of x is equal to 0 for some x in the domain. So we are saying that there are no roots. So you have to choose c to be 0. You have to see that there exists no x such that f of x is equal to 0, or you have to say that f of x is not equal to 0 for every x. This is our aim. So for that, choose c is equal to 0, and then f on closed interval 0 b be a number inside open interval 0 3. Okay, since f is continuous on closed interval 0 3, it is given that f is continuous on closed interval 0 3, it will be continuous on a subinterval 0 b, closed interval 0 b. Now since f of 0 is equal to 1 given, strictly greater than 0, we simultaneously have f of b to be strictly greater than 0. But b was anything in open interval 0, closed interval 3. So that means we have proved what we are asked. So you can go through the question and follow the steps using your own logic, using the intermediate value theorem. It need not be the same statements which are given inside the text. You can use your own logic and also try the exercises 1, 2, 3, 4, 5. Then you do 10, 11, 12, 13, 14, and 15. And you can try out other questions too inside this set of exercises so that you are becoming very familiar with intermediate value theorem. It is a very important theorem. You have to definitely follow the theorem because there are plenty of use of intermediate value theorem that comes into picture when you're dealing with problems. We are going to deal after this, and the next section is increasing and decreasing functions, section 3.2, and that we'll see in the next video lecture. So thank you for watching out, and please go through the lecture and do make clarifications if there are any, because this is a very important part of our chapter. So thank you.